Hello everyone, welcome to another episode of Yo at Home. So, we want to talk about what the mass defect is. The mass defect, very specifically, if you take the mass of all the protons and neutrons put together inside the nucleus, and if you subtract from that the actual mass of the nucleus after all the particles are settled in. So, here's all the particles that make it. Sort of like putting bricks together to make a house. You put all these bricks together, weigh each one separately. Then you weigh the house. Well, you would expect the house is going to weigh the same as all the bricks you used to put it together. But in an atomic nucleus, this is not the case. When you weigh all the parts you took to put it together, and then you weigh the completed structure, you are missing some mass. And this is called the mass defect. So it's a positive number equivalent to the energy given off when the nucleus formed, based on the idea of E equals mc squared. Let's take a look at an example problem. All right, so if I take a proton and look at this in atomic mass units. Now, atomic mass units I'll define in a second, but it's 1/12 of the carbon-12 nucleus. So it's the average mass of a nucleon. A proton has a mass of 1.0073 atomic mass units. A neutron has 1.0087 atomic mass units. The mass of the helium nucleus is 4.002602 atomic mass units. So let's see what the mass defect is. So if I take the protons, multiply them by 2, because there are 2 protons and 2 neutrons in the helium nucleus. So I take the protons, multiply it by 2, get this number. Take the neutrons, multiply it by 2, get this number. Add those numbers up. That is the total mass of the constituent particles of the helium nucleus. So all the bricks it takes to put together the helium nucleus, that's the mass of it. But when I take the mass of the helium nucleus, it's a smaller number. That's the total mass of the nucleus. When I subtract that, this number I get right here, that is the missing mass, known as the mass defect. Okay, so the mass defect then, we want to look at what the energy lost is. So the first thing we need to do is convert an atomic mass unit to kilograms. Now you can imagine by this point in the course this is not going to be hard. 1 AMU, an atomic mass unit, is the mass of a carbon-12 atom divided by 12. Therefore, it is considered to be the average mass of a nucleon. 1 AMU is given as 1.6605, and we could carry that to more significant figures. They've gotten this quite precisely, times 10 to the minus 27 kilograms. So, to convert AMUs to kilograms, what do you think? We multiply by what? We multiply by 1. What form of 1 are we going to take on this time? Well, that's the 1 AMU is 1.6605 times 10 to the minus 27 kilograms. So we have the mass defect of helium, 0.029398 mu u, times 1.6605 times 10 to the minus 27 kilograms is the same as 1 u. So that equals 4.88 times 10 to the minus 29 kilograms. And that brings us to the concept of binding energy. Binding energy simply is E equals mc squared. It's the energy lost when a nucleus comes together. Binding is the energy lost when a nucleus comes together. Is there any place where you could look and see binding energy happening right now? Hey, it's daytime. Go outside, look at the sun. The sun shines because of this binding energy. All these nucleons falling together and giving off energy, that's what makes the sun and all the stars shine. So, pretty important stuff. So, the binding energy, using the mass defect of helium, because that's actually what the sun is forming, E equals mc squared. Take the mass lost, okay, the mass defect in kilograms, after you've multiplied by 1, take the mass lost, multiply it by c squared, 3.00 times 10 to the 8th meters per second, and you will get 4.39 times 10 to the minus 12th joules. For a single atom coming together, that is a lot of energy. And that's the binding energy. And it's also why the sun shines. And it is created by the strong force. These particles coming together, when they feel the strong force, they are pulled together with such violence, such intensity, that energy is given off. That energy given off, that's the binding energy. Now, if I ever want to take those particles apart, well, I have to input that much energy, this much energy, to the nucleus if I would want to separate those particles into their individual hydrogen atoms. It's a lot of energy to put into a single nucleus. It's a lot of energy coming out of a single nucleus. Take a look at the sun. That's why it's so shiny. Hope you got that. This has been another episode of Yo at Home. Hope you enjoyed it.